All right. So, Andrew, that was an awesome talk. I learned a lot from that. It's a hard topic to summarize, going kind of from a kind of a basic level to a more advanced level. So I really appreciated that. And thanks for the organizers for allowing me to present today. So I'm a climate scientist. I'm interested in many questions about climate. So there's one of the most impactful consequences of human influence on climate is sea level rise. So it's, and the most large contribution to sea level is from ice sheets. So it's reasonable to ask, how confident are we in sea level rise predictions that come from ice sheets? So I got involved in this question through kind of a series of projects that I'm a participant in. So let's see, I don't have expertise in many aspects of this problem. So I just want to acknowledge one. So there was a DOE SciDAC project on developing advanced ice sheet models. And part of that included an uncertainty quantification part. So I will be presenting some of the kind of characterization of this problem that came out of that effort. There was a NASA project that one of the sources of uncertainty for ice sheet modeling is the bedrock topography. And that's sparsely sampled. And so I have a project where we were representing the uncertainties in that. And then this NSF one, we were asking this question of how are you going to get large contributions to sea level? Like, what does physically have to happen in order for that to take place? So these all involve collaborators that are mentioned, but that's not the complete list. So I will list other names as well. I wanted to first kind of step back. The application of uncertainty quantification methods to climate questions is still in its infancy. We really kind of are just, not many people are involved with it. And I would say we're also not all that confident that we're getting answers that are meaningful, for policy. So I would say mostly this is for ourselves, like how would you go about this problem? And eventually we'll learn what is the right set of observations, what are the right experiments, so that we can really test our predictions in climate models. So, I started really on this problem through an atmospheric, like the predictions of global mean air temperature and the role of clouds. But here, I learned a lot actually about uncertainty quantification through my involvement with these projects. So that's, I will start broadly, but then dive into two problems that deal with sea level rise. One is the problem of initial conditions for ice sheets, and the second one is the characteristics of the marine ice sheet instability problem. So when I talk to program managers or more broadly to people about uncertainty quantification, usually there's this glazed look over the face, because it's like you could talk about all the different sources of uncertainty. It's like Andrew's talk, how many different parameters, how many different types of processes, it's just enormous. So for me, the uncertainty quantification objective, the scientific objective, is to simplify what in the world we're talking about. So what I like is this talk or this presentation that Richard Feynman gave in it was a press conference explaining what they learned, why the Challenger exploded on launch. And in this presentation, he had a glass of ice water, and he took an O-ring and he deformed it, and he put it in the ice water, and he took it out, and he unscrewed this bolt that was holding it together, and he said, see how it retains its deformed shape. so that when you get too cold, basically these O-rings weren't performing basically the way they intended it to. So what I like about, as kind of as a metaphor for what we're trying to do, is that we have a complicated system. It has all kinds of moving parts. But ultimately, if you want to understand something important, you want to reduce and be able to provide confidence in your understanding of why, have an answer in your mind. It has to be a really simple, something that you can almost hold up, right, and inspect. So yes, we have complicated models and everything, but I think part of the point is to really identify what is the thing that will determine most the consequential outcomes of these models. So uncertainty quantification for climate can't be approached just from a mathematical point of view, from sitting at a statistician at a desk or a mathematician. Even a scientist can't actually answer these questions without the help of the math people. So I think this is a really good problem where you really need kind of deep integration among the people who know various pieces of this puzzle. So I guess that's one of the message I want to make from this talk. Hopefully it will come clear. So the characteristic of the problem we're trying to solve is a prediction problem for which we don't have observations, but we do have some history. So this is the IPCC CMIP5 multi-model predictions of future climate. We have a historical period over the last, let's say, 100 years, and our models, almost by design, let's say, are replicating that record, but that when you extrapolate out into the future, they diverge. Well, of course, they diverge because of different forcings, so that's what the different colored lines are. But even within one forcing, there's quite a bit of spread among these model predictions. So you can kind of break this problem right into kind of an inverse part, and this is, maps onto the uncertainty quantification space as an inverse UQ, where you take observations and to determine a realistic climate model. And then you take that climate model and you basically integrate it forward in time with maybe some forcing, and that's the forward propagation of uncertainty. So that's the general characteristics of uncertainty quantification. And so currently the testing process is done by experts, not necessarily in a formal way, but one can begin to ask how you would do it formally. And so you could say the problem in the inverse uncertainty quantification is to estimate a set of model parameters that are involved, let's say, with clouds. And we're going to select or reject different combinations of those parameters given observations. And this here is a test statistic, right, that determines whether we accept or reject. And there are a lot of, let's say, challenges in doing this for a climate problem. One is that this covariance matrix determines a lot of what the answers are, and you can't go about this. You can't just take observations and create a covariance matrix. It mathematically is ill-posed, and we need to spend a lot more time thinking about how do you define the weights of how you what is the significance if you get a discrepancy between a model and data? How do you weight all those discrepancies together? That's the job of this inverse covariance matrix. The other challenge here is that this operation, getting a climate model to reproduce observations, is expensive. So to integrate the 1 degree CAM, the latest version, I guess, is $60. So it's about 1 cent per computational hour. So you can figure out how many computational hours. But it's expensive, but not ridiculous. If you go to a 1/4 degree, which is the one that Michael Werner only wants to look at, a 4-year integration costs $20,000. So that's humbling. Now, for ice sheets, the time scales for equilibration are extremely long, probably longer than 40,000 years. But we had a talk earlier this week where they were using 40,000 year integrations of a shallow ice approximation model. So if you do that same integration with a higher order model, which is not necessarily all that we can do, but it's still it's a very good model, at 1 kilometer for Antarctica, it costs $600,000 computational time. So you have to think about this problem in different ways. So part of the Department of Energy project called PISCEES involved a large cast of characters that was to create advanced flow models, and part of that effort was to create an adjoint ice sheet model that was a way of doing the inverse problem very cheaply, so that you can cut out that equilibration time. And so that had implications for how you do uncertainty quantification for this. So let me also kind of say a little bit more broadly where we are with sea level rise. Over the last century, sea level has risen 20 centimeters, and it's been pretty much a steady rise from tide gauges, and then as you get up into the satellite era, you can see that the rate has picked up. There was some controversy about why the rate kind of changed sign right when you change the observing system. And that was a little bit unresolved until this year. There was a paper that came out that did a budget for the last, I guess, decade. And this is actually really remarkable in terms of a feat of observation and science, in that we have basically all our different observing systems, and the mean of that is given by the red. And if you do kind of a budget of different contributions from different ice sheets, from the thermal expansion of the ocean, if you add all those together, you get the red line. And the fact that those two line up so accurately is just remarkable, and should give us a lot of confidence that we know a little bit about the processes responsible for sea level rise, including global warming. Of course, ice sheets are contributing to this because the atmosphere is warming and the ocean is warming. Going for our projections, the IPCC expects, depending on the forcing scenario, anywhere from about, 60 centimeters up to a meter rise in sea level by 2100. And this is considered a conservative estimate, in part because we have a hard time quantifying the ice sheet contribution to sea level due to the changing in its dynamics. So some aspect of that is reflected in that number, but not necessarily fully. So with these advanced computer models, one of these is observations of surface velocity, and one is a model. And the way to tell which one is which, and this is what I have to do, is that there's missing data in the observed surface velocity. And so right here, there's missing data, and this is the observed, whereas the model actually predicts velocities there. But one of the, from an uncertainty point of view, maybe this gives you a lot of confidence that we can initialize our ice sheet model exactly, almost precisely with what we observe. We use all our observations to get something that looks really realistic. But this comes with a bargain that's not good for predictions. And that is a lot of what determines that solution is the properties specified at the bed. And what kind of bothers me about this, it's a great feat to do that calculation, and it required a lot of advanced computational thinking and so forth. But we know that, so there's a part of an ice sheet, 90% of its mass loss is through ice streams. And those are these higher velocities, and this basically, the flow of ice gets up to several kilometers a year going into the ocean. Whereas in the interior, it's around a meter or 10 meters. So it's orders of magnitude acceleration as you get close to the coast. So that dynamic change going from creeping flow to basically stream flow is really kind of the magic of what ice is, right? It's a nonlinear fluid that has this potential to both to just accelerate, right, and create these sharp boundaries between where it's flowing fast and not flowing fast. So, but in order to get that, wherever we have fast flow, you basically see that the basal friction, in this case red means low friction, and you had to basically specify these sharp boundaries, right? So you had to pretty much give it an answer in order to see the answer. So in climate, one of the challenges there is that we guarantee that we need to get surface air temperature, but the compromise is this, and this is particularly true before we had good observations of cloud distributions and properties, was that you could always put all your errors into the clouds. That you can almost do whatever you want because you guaranteed that you got that surface air temperature, right? But the leading source of uncertainty for global warming is cloud properties. So for ice sheets, it's going to be the specification of the basal boundary condition. So the problem is that this is a fixed quantity for doing these predictions. And that obviously, if you're trying to understand the potential for evacuating huge swaths of the interior of Antarctica, you're going to be evecting ice into these higher frictional zones, right? So that's probably not good for uncertainty quantification. So one way of going about this was, this is like uncertainty in the initial condition of the ice sheet, and the initial condition is really the specification of the basal traction field. Now that they had this adjoint of the ice sheet model, they could calculate also a Hessian. And the Hessian tells you something. So if you have an objective function, let's say getting the surface velocities like observed, you can ask how strongly are these observations constraining the basal properties. And you can, so if you take the eigenvectors of the Hessian matrix, it gives you some idea of how you can vary the basal traction field to get something nearly the same solution for surface velocity. So it gives you kind of some wiggle room, right, with how you can make changes or perturbations to the basal traction field, so you could maybe do some experiments. So these things, so these are eigenvectors. So the first, second are these large scale features. When you get to the 4,000ths, you have a lot of like micro scale features. So that's useful, I guess. So one of the challenges is you can ask, well, how many of these are required to adequately map out if you wanted to sample this space, right, and to play out some scenarios, how many of these would you need? And the answer is independent of model resolution. So that's where there are two, one did it with like a million different grid points, and the other one did it for 500,000 grid points. So independent of the number of grid points, you needed 4,000 of these things. So you now have an uncertainty quantification problem that is 4,000 dimensional. And so, and you don't know, any of these could be important. So one of this, okay, so you could use, say, adjoints to define that problem, which I showed you. You could also do it in a more stochastic way, where you can kick the system around. You could just have artificially, define KLE modes and just run the model and learn how, when you perturb this basal traction, what happens to the flow out of the boundary. And so you have all these kind of ways that you lose ice mass by imposing these things. And then you can learn how each one of these patterns affect ice flow, and then recombine them in ways that tell you, I think this gets back to the Richard Feynman point of this exercise, is that when you hit it with this arbitrary kind of different types of patterns, the model itself, the physics of the model says, well, we have certain outlets, and we will lose mass through those outlets. And each of these maps can be combined to show that if you change basal traction in each of these outlets, you will get this mass loss. So that, I think, is kind of neat in that the physics of the system helps simplify or pick out kind of the modes that are most important. And so there's a statement made by Wilcox, Karen Wilcox at MIT, that says, in a linear system with a scalar quantity of interest, that the uncertainty is one-dimensional. So even though we know we've just defined uncertainty as being this 4,000 dimensional, I think as a scientist, I want to find that one dimension. And I know also it's going to be some sort of linear combination of all these things. So the next task is, well, how do you find that linear combination? So this is kind of the strategy we outlined for ourselves, that there were so many demanding aspects of this problem that we never fully implemented it, but this is the cartoon of what we were trying to do. So we have our adjoint, we can estimate the basal traction parameter, and you can find the map estimate. So that's the best estimate of basal traction, and I've shown you that. And then we want to perturb it in certain ways, and that's our uncertainty. We have different ways of perturbing it. We have an intrusive method using the Hessian, or in a non-intrusive way, that was with this KLE expansion. So this is basically a kind of a basis set to explore, but it's really high dimensional. And the thing that will simplify it is that these expressions don't really have anything to do with future sea level rise. We didn't really do a sea level rise experiment there. All we said was, how can you change this basal boundary condition to match the observational data? So there is some sort of active subspace that is a strategy that that we have early indication will work, but you have to kind of go through this process by which you do a sea level rise experiment. You hit the model and you go out 100 years. You learn a little bit about which parts of the ice sheet are changing. Then you can learn more about which parts of the basal traction were important to that, and that will help reduce the dimensionality, because you find this kind of what's called an active subspace. And so you kind of go between doing these sea level rise experiments and refining which dimensions you need to explore further that will determine most the uncertainty in that sea level rise prediction. So I think that this is the Richard Feynman, finding the O-ring involves this process of reducing the dimensionality down to that one map that I think we're after. So we're not there. I don't have a one single map to show you. So now I want to move on to a different question, which is how might we get a significant rise in sea level? So that we think is through a marine ice sheet instability. And there's significant portions of Antarctica where the bed is below sea level. And so we also know that bed topography is an important determinant of ice flow. And so our initial focus was on describing the uncertainty in the topography and its potential impact on the marine ice sheet instability. But through this experiment, through kind of chance, we learned also a really important lesson about the dynamics of this marine ice sheet instability, and that the big conclusion is that the mass loss rate is really sensitive to the amplitude of forcing right across that stability, and I'll show that, but it's a pretty amazing result. So these are gravity observations through different years, so that you probably can't see, but this is 2004, 5, 6, all the way up to 2013, showing mass loss around Antarctica, and it's unevenly distributed, focused on West Antarctica. And that's not good news for us because, in particular, West Antarctica contains the Thwaites and Pine Island basins, and those basins are below sea level. So this is a map that you can't see from space. This is the bedrock topography of Antarctica. East Antarctica has a lot of highlands, mountainous areas. Wherever it's blue, it's below sea level. So even though the ice sheet sits above sea level, and it's about 2.5 kilometers thick, it rests on the seafloor that's over 2,000 meters deep. So this is a cross-section of Thwaites Basin taken from an airplane using ice-penetrating radar. That radar sees through the ice sheet to the bed, and it gets high-resolution information about the topography. It can see where there's water. It knows where there's sediments. All these are important boundary conditions for ice flow models. When you're running an ice sheet model, you need to know to initialize it, surface topography and your velocities. We use that to invert for the basal properties, that friction. But it's important to realize that there's a lot of things going on at the bed, such as melt, and there's water production, which can lubricate. If that water is in sediments, it becomes very deformable. But if it's crystalline rock, maybe not so, right? And so when we specify that, we would much rather have a sliding law for the bed, but we don't yet. We also would like to have a hydrologic system underneath the bed, and that's kind of the latest, greatest thing coming to ice sheet models is the subglacial hydrology. So anyway, this marine ice sheet instability occurs because the bed is deeper into the interior than it is toward the coast. And that's not quite an accident. This is actually kind of a general property of a lot of ice sheets, because ice sheets are so, there's so much weight that they depress the earth underneath them. So as you get a thicker ice sheet, it depresses the earth more. What happens is that the flow of ice out to the front is proportional to the surface slope and its thickness. So that if you retreat a little bit, you get into, the slope will both increase and you get thicker ice. So as you go, so where will that stop, right? So in this case, and it doesn't. So it's a two-dimensional theory. So maybe one of the things that stops it is that there are pinning points on lateral sides of an ice stream or something that stabilize it. So one of the kind of experiments you can do is, you can say, improve your representation of bed topography and run a two-dimensional representation of all the topography and with an ice sheet, and ask what is the potential for this West Antarctica to experience a marine ice sheet instability. So this is work that a graduate student, Scott Weibel, has done primarily, and then we're advised by myself and Christina Holba, and we're making use of this ice flow model in conjunction with Dan Martin at Lawrence Berkeley Laboratory. So the bicycles code is an adaptive mesh refinement that uses kind of an approximation to the flow equations that make it particularly computationally efficient. Only $2.50 to simulate per year, so that's pretty good. So the domain we focused on is the Thwaites region, outlined here in black, which is in West Antarctica. The image here shows the surface velocity. So we use adjoint of the model to initialize it, to specify that boundary condition. But in this case, we just held it fixed, and just that, because that's the state of the art at the moment. We came up with an experiment design where we gradually ramped up ocean melt to identify where was the point of instability. And so we basically ramped up this melting very slowly, and then when the ice mass loss rate started to pick up, we turned off this anomalous forcing and just let it go without any additional forcing to see if it would do this marine ice sheet stability. So this is a melt rate that was applied very slowly over hundreds, thousands of years. and until we find this point where we think that the rate, all of a sudden, this instability picks up. And we tested 2 points that were 10 years apart, one at year 250 and another one at 270. If you pick wrongly and you pick too early, so for instance, if you thought maybe this was the point, which is year 170, and you take away the anomalous forcing, basically the ice sheet just stays there. It's stable, right? It doesn't, but if you pass that endpoint of instability, this is, each line is a different point in time. Basically, this thing just keeps on marching back. And we did this several times with different initial conditions and different melt profiles, and you get slightly different answers, but I'll try to simplify my presentation here by just emphasizing the results that came out of removing that additional melt at year 260 versus 270 and asking what was the consequence of those two initial conditions on the retreat. And this is where we got a big surprise. Maybe this is a movie. I'll skip the movie. Oh, it's going. Wow. I'll just mention part of the important thing is that as the grounding line retreats into the interior, it gets hung up on these little bumps. But the marine ice sheet instability is a powerful function of ice sheet thickness to a power to the second to the fifth power. Gerard Rowe at University of Washington has this nice paper where he kind of explains how powerful the marine ice sheet instability is. So that will become relevant in a moment. Well, one of the surprising things was that initial 10 years of additional melt, and then we removed the forcing, caused, and it had additional mass flux out the front, and so additional mass loss, and that was sustained for the entire run. So over basically 2,000 years, if you look at the retreat at each point along the way, and you compared it to starting at year this collapse at year 260 versus 270, that the 271 had accelerated and maintained that additional rate for the entire run, even though there was no additional forcing. So let's see. I want to. One of the. So let me just say that. So that scientifically, that is a big deal. What that says is that whatever we're doing as a society to ramp up greenhouse gas forcing, to warm the ocean around Antarctica, the faster we do that, the faster sea level rise will be for the next several thousand years. If we slow the rate of warming around the ocean, then the rate of sea level rise will be smaller. Only because of how fast we push it basically off the cliff. Because those feedback swings are really sensitive to what's retaining the ice at present, and if you push it off fast, then that will cause a retreat that sustains itself for a long time. So the bed topography is also an interesting thing, and I will kind of skip. I will say that we used a statistical methods to represent topography that we did not see with the airplane, but is consistent with the observations we had with the airplane to roughen up the surface. And so this is the same domain. It caused, we needed more forcing to reach that point of instability. And the grounding line where it reached that instability was further inland. But, now this is the puncher here, which is the collapse rate was even faster than the smooth bed. And that is because you could think of the system as being constipated. And sorry for that image, but all that gravitational potential energy of the ice interior is really what forces the ice mass out. So if you have a rougher bed, if you increase basically the roughness at that lip, then it's harder to get that ice that's in the interior out at any point. But once you pass that point of instability, that is a powerful function of that those feedbacks are just overwhelming, such that the roughness doesn't matter, and you retained all that potential energy, so that stuff just explodes out, so I think so. If you look at sea level rise, the equivalent, the rate of sea level rise over this several 1,500 years without any additional forcing was highest when we had this rough bed. It was second highest when we hit it a little extra harder across that instability time, and they all got to the same point eventually, but it got to the higher rates of sea level rise, or more sea level rise quicker with the roughest bed. Okay, so what I find interesting about this problem is that the importance of learning from model predictions. So this is going into global warming with air temperature, in terms of sea level rise, doing these experiments where you actually do these collapse scenarios actually teach you a lot about what are the relevant observations that you need to get right. And the other aspect is the extent to which we need to know more about boundary conditions. So this is, in some sense, physicists don't like to think about boundary conditions. We like to think about physics. And boundary conditions come from observationalists. But there's the interplay between these things. So if the physicists want to play with uncertainty in their predictions, they're going to have to talk to the people who generated the data to understand what is uncertain about them. So I think that's an interesting kind of, let's say, side story to the sea level rise problem. I think that's it. Thank you.
So that was very interesting and a little scary. I guess the comforting thing is that your timescales were really long, so that the sea level rise is going to take thousands of years. Were you? I didn't quite get. Was the forcing? It was forcing it from the ocean heating up. Is that what you were forcing with an ocean warming?
So the model didn't really have an ocean. We basically applied a melt rate to the ice shelf. And then that thinned the ice shelf, which created additional reduced backstress to the ice stream. There are a lot of details, right? Ocean dynamic details that determine how heat gets delivered to an ice shelf. So that's important physics and dynamics to figure out. The other thing is that this model doesn't include subglacial hydrology. So as you retreat, the hydrology actually may act to stabilize a system. So there's lots of things that we haven't included. So this, I would say, is an exercise, but it's a revealing exercise.
Thanks. So nice talk. Lots of great things to think about. The one thing that I guess you didn't mention was the ice cliff instability, which is separate from the marine ice sheet instability. And that has to do with the uncertainty in the physics of the ice and how it cracks as it's sitting there at a 1 kilometer cliff.
Yep.
And of course, Dave Pollard and Rob DeCanto have looked at that. And it's one more thing to add on, and it makes it go even faster. So it makes it even more scary.
Yeah. So in this case, the ice. So there's one result I didn't emphasize is that depending on the vertical melt profile that you specify, either the ice shelf interacts with pinning points, little islands, or not. And if it interacts with these pinning points, then it does slow down the overall melt, the rate. But there's lots of additional physics, such as the calving law, which is, like you're saying, the kind of our understanding of how the calving physics operates will also interplay with this. And this model doesn't include any of that additional dynamics. So there's lots of little things to explore.
So, Charles, this is really an interesting talk. I'm going to ask you to say something that you might not want to say. The way I understand some of your experiments, you ramp the forcing up to some unstable to some point, and then it stayed constant after that.
No, it's removed.
It's removed. Is there any way to tie this into stabilization targets to draw some analogies to to future scenarios, like the Paris protocols or something? I mean, are these forcings, much greater than those targets, or are they less, or what, can you give me some context?
So there was
that?
a group of scientists thinking about the sea level rise problem, and one of the outcomes that I liked the most about that was this question of what forcing will it take to get to push it across this instability. And I think that's a really useful question for our community to be asking. And so it basically, it would say what amount of, let's say, ocean melt, but you could think of other aspects to that, of what will it take. And in this case, it was about 13 meters additional ice melt, which is about 1.33 degrees. If about 1 degree, it melts about 10 meters of ice per year. So it's not all that much warming of the ice. Yeah. But yeah, I think it is. I think that is a really, from a risk point, you say, what are we how much forcing would it take, and what is the what conditions in the ocean would need to deliver how much heat? And I think, and what were the processes that would do that? I think all those are reasonable questions to ask. So I like that. I like that framework to be thinking about it.
I also want to say, if you want to ask Andrew questions, that's also perfectly valid too right now. So.
Okay, well, just related to this, even before the point at which you get to a marine ice sheet instability, I'm trying to understand the timescales in the system. So, with global warming, we're already pumping a whole bunch of heat into the Southern Ocean and the region around Antarctica. If we turn off our CO2 forcing in 50 years, how quickly does the forcing, as seen by the ice sheet, actually turn off?
Excellent question. There's a lot of processes, eddies, the fronts. There's all kinds of things that could prevent. So it's interesting. So the Ross ice shelf has a lot of heat going in and the same amount of heat coming out. For Thwaites, all the heat comes in and it all melts, right? So there's a lot of boundary layer processes that dictate the heat exchange. So just warming up the ocean doesn't necessarily say that you would get ice melt. So there's interesting oceanography and all kinds of things that to be considered.
Very interesting talk. Again, I think this is maybe slightly related to timescales. Does your model deal with allow for the sort of the bounce back of the bedrock when there's sort of excessive melting?
Yep.
There's that slow bounce back,
Yep.
which can actually counter some of this.
So no, the answer is no. And I think it's an important thing to take into account. So there's more recent geophysical observations show that this part of the Earth's crust is very much more like a sponge, like that bounces back really quickly, like in 100 years or something like that. So that feedback would be a very stabilizing effect on this, and so that's not included. So that's a very good point.
Are we taking questions for the first talk as well? Yeah. Okay, so this is actually for Andrew. So I'm a bit curious because, most of it was very nice talk, but all of these treatment of parameterization is based on the assumption that we want to describe the PDF of the model. But so my concern is about how can you convene the fact that when you treat a model under climate change, so actually the model is not longer an autonomous system, is driven by an external forcing which is time dependent. So the mere existence of an attractor for that type of model doesn't make much sense to me. So there is not an invariant distribution. So maybe it's a too naive and theoretical question, but I really don't know how you can make the two things together.
So I guess the way to think about it is the climate as an attractor changes over time. So climate change means the attractor changes, right? So the question is, are we going out a sample in our model because we're pushing it in ways that we haven't before? Well, at the process level, we're probably not pushing it any way we haven't pushed it before, because the variability is very large anyway. There's a few extreme points that we saw, you know, some of the things that Michael Wiener was talking about yesterday with the extremes of temperature and precipitation. But the hope is, again, if we go from individual processes that we know, then the model hopefully will alter the attractor over time. And I don't think under climate change that a gamma function won't work for cloud microphysical parameterization of a size distribution at the small scale, right? Because we test that on weather states that are all over the place. So if you think of weather states as the global climate change is a series of individual climates that sort of are moving around and evolving, then we sample those climates today on the planet. It's just the overall distribution is changing. The whole attractor is evolving over time, but it's not specified. We don't specify the attractor, right? We're specifying the fundamental processes that the attractor is an emergent property of the system, climate. I think in that sense, that's kind of where we go. It's the physics that govern it, and that we hope, again, we constrain all those physics at each level by the fundamental laws of motion and things like that, and the energy balance kind of pushes it into a place where the overall climate attractor is new.
Right, one last, all right. You're going to have to be really quick.
So, first of all, I think there are real problems with this question about how we define attractors. But I have a simpler question, which is simply, when you say we don't need to know the weather today, I think there's real problems with and I completely agree with the distribution issue, but we do need to know things like the initial conditions for processes which have time scales more than 100 years. And particularly, we need to know things like if we're in an ice-covered Earth or not an ice-covered Earth, the Bedico cell. And I really struggle with trying to figure out, how do I define climate as a district? I want exactly your definition, but how do I fold in the fact that I do need an observation of some kind of macroscopic property without conditioning it on the state of the system?
Well, there are obviously initial conditions. It depends on the scale, right, which is what you're saying. So yes, we don't need to know the weather, quote unquote, but we do need to know the distribution of ice sheets. We even need to know, say, the distribution of continents, right, on a really long time scale, which is what you're getting to with like a snowball Earth, and the flux output of the sun, which changes over. So there are time scales ranging from, hours, the current state of the weather, to hundreds of millions or billions of years that we specify in the models, up to the solar output, the solar constant. So yes, for certain problems, what is weather doesn't matter. The initial conditions do matter very much. When we're running 100-year climate simulations, how we initialize the ocean matters a whole lot. How we initialize the ice sheets matters a whole lot. It is still an initial condition problem at those time scales.
Wait a minute, we got another question now. So we got to, you guys talk offline. Sorry. We got one more question
yes,
over here.
I'm going to make it really short. It's a 10-second question for Andrew. So as an outsider, I'm not a climate scientist. It took me years to figure out what parameterization means. And I learned a lot more about what all goes into it, but I was wondering, is there a historical reason? Why is it called parameterization? Because it doesn't seem to represent what's actually being done.
Because it has a whole bunch of parameters in it?
Yeah, but it's so much more than choosing parameters.
It is. I don't know. Let's go figure that out.
It's really confusing.
Thank you very much. Let's thank